Hey everyone, welcome to the wolfSSL live webinar. Getting started with wolfTPM presented by wolfSSL Senior Embedded Software Engineer David Garske. My name is Cameron and I'll be moderating the webinar. All attendees, you will be in listen mode only. If you have any questions, please use the Q&A box and we will host a Q&A session following the presentation. Our webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I invite you all to follow us on Twitter at wolfSSL, as well as our other social media platforms. Also, feel free to email us if you have any additional questions. And now I'd like to give a brief overview before we move into the technical presentation. Today, wolfSSL secures over 2 billion connections, and we have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by a strong partner network that we're extremely proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification, and FIPS ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, and a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support and commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And with that, I'd like to turn it over to David to talk about getting started with wolfTPM.
Thank you, Cameron. So I'm David Garske. I'm a software engineer with wolfSSL. I've been with the company over 9 years, and I was a client. I was a customer before that. So a lot of exposure. I'm also the author of the wolfTPM library, which is what we're going to talk about today. So wolfTPM is this component here, and it only relies on wolfCrypt, and even that is an optional component, which I'll go into. And I did want to take a moment to call out wolf PKCS11, which is an HSM standard, and recently we developed a TPM backend for that. So you can make the TPM look like a PKCS11 HSM. I'm not going to demonstrate that today, but it is all open source. It's on GitHub. And well, I guess I could talk about it more later if there's a question on it. But so I wanted to give a brief history of the TPM 2.0 progression of the standardization through the TCG group. It was developed far back in 2003 with the original specification, but everything I've developed and everything that we're going to talk about is TPM 2.0. And that specification was released in 2013. It quickly adopted, and that's pretty much what you'll find on all your, machines that have been developed, like Intel type hardware that's been developed after that. Now there are several vendor options, and we'll go into all those details, but the TCG is made up of a bunch of companies, including the chip vendors, but Intel, Microsoft, and IBM were all part of that. And the effort was to standardize the cryptographic interface, thinking about protection of keys. So again, it's commonly used in like x86 Intel systems for measured boot and protection of keys. It's used in UEFI, Linux in their disk encryption system. It's also used with Microsoft Windows in the BitLocker. So Windows uses the TPM for all the protection of the keys with BitLocker. There's been a trend that's happened, I would say, for at least the last 5 or 6 years where TPMs are starting to be used in embedded IoT devices. And we're also seeing a lot of standards that call out specifically using a TPM for protection of a key. And it's because it's designed into its core, right? And it automatically provides key protection. So what can you do with the TPM? Well, you can securely generate, store, and use keys, lots of different types of keys, so asymmetric and symmetric keys. It has a non-volatile storage for keys in one-way counters. Basically, it's an area where you can store any type of data, and you can store it securely in addition to keys. There is a key hierarchy system in place where each hierarchy has different privileges to separate the keys for purposes. It has a built-in true random number generator, dictionary attack prevention mechanisms, like if somebody's trying to brute force, and you can quickly reload keys. So the TPMs have, I would consider it a limited amount of non-volatile storage, and there's ways they've made it so that you could actually have thousands of keys if you wanted to store them locally. So the three hierarchies are platform owner and endorsement. Most of the time, the owner hierarchy is used for creating and storing keys. The platform one is I would say is something that not the owner, but like the manufacturer or somebody who has more permission. So out of reset, the platform hierarchy would be available and it would normally be locked down so the user couldn't access it. Each hierarchy has their own seed, and keys created under them have different policies associated with them. I'm not going to go into too much detail because it's fairly complicated, but keys are generated using that platform seed, a template, and some random entropy, and it uses an HMAC-based key derivation function. Now, primary keys are must be created first before you can create or import other keys under them, and the primary keys or one of those three types of primary keys: platform owner, endorsement. There's also a null type hierarchy for ephemeral keys that are just one-time use that might get tossed out. So one of the cool things that TCG did is they developed a PC client specification. So if you're using a TPM that's part of the PC client, I think the latest is 1.05, it actually specifies that the pins, the form factor of the chips and the pinning of those is all compatible, which is pretty cool. So it's easy to switch between vendors if you decided, so you have more options. All of the TPMs expose the same standard set of APIs and respond to commands and return responses the same way. And vendors can add their own custom ones. And the transport is typically a SPI or I2C interface. And there's also a standard for what that interface communication looks like called the TIS. And wolfTPM actually implements its own transport interface layer. If you're using Linux on something like a dev TPM0, they already have that built in. Okay. And security, so designed with private key protection and resistance to side channel attacks and glitch resistant. What that means is these chips have physical protections in them to prevent somebody from being able to access those keys, using like modern techniques to extract them. So this is the set of algorithms. Most of these are in all the TPMs. The ones I've listed here are in all of the latest TPM 2.0 modules. SHA-3 might be optional. There are some other algorithms that you will find that are optional as well, but this is kind of like the normal base set that we see. These are the vendors that wolfTPM supports and the chips that we've tested with. There may be some other vendors, but these are the ones that we work with. In theory, they're all compatible, right? So if you design and develop a TPM module that's a 2.0 module that's compatible, it should be able to just be swapped in and used. And I've seen that as well. So for example, Nations Tech, when they took our library down and tested it, they were able to use it without any changes. I don't physically have one of these TPMs, but I do have all the other ones. So for this webinar, I put together this spreadsheet, which outlines the interface available, the storage size, and the performance. And I reran these on all the chips before the webinar here, and I bolded the ones that are better. So I know I'm totally impartial to the vendors. I work really closely with Infineon and ST, but they're all good modules, and they all have levels of FIPS certification in them. I will say that these modules can also be used to just offload cryptographic operations. So you can use them just like a crypto coprocessor for ECC and RSA, and some people do that. The main, there's lots of use cases which I'll go into, but I guess the main thing to look at here is, the size of the MV really is how much you can store on the chip. Again, it's secure storage. Typically, like if you were going to use that, you would persist keys there, or you might store a certificate there. And this is operations per second for like RSA, keygen, private operation and public operation, and RSA, keygen, sign, verify, and a shared secret. They all perform very well. again, we'll if you want these slides, just email facts at, and you can get these and look at them more. So let's go into wolfTPM. It's an open source library. It's out there on GitHub. Yeah, it's GitHub/wolfSSL/wolfTPM. For the cryptography underneath that requires, so for for example, to do parameter encryption, you need AES-CFB. You need a software implementation of that. You also need an HMAC, with SHA-2256. And so for that, we use wolfcrypt. Now, if you wanted to build the library standalone without anything, then you can. You just won't be able to do parameter encryption. You won't be able to do things like import an external private key. So it's fairly limited. But if you're just using it for like measured boot where you're updating a PCR, you don't really need those things. So, and the code size can be very small. The smallest I've seen wolfcrypt with wolfTPM was about 20K, I think. wolfTPM on its own, it could be as little as like 4 or 5K. I mean, there's really not much to it. So, but what we did, TCG, the specification actually defines a set of base APIs, and you'll see them labeled TPM2_, and they're all in TPM2.c. And we've implemented 100% of those just as the TCG, specification outlines, and they all have a structure with an input and output parameter, and that's it. And they really assume that it's like one TPM on the system. And so what we did was we also developed an extended wrapper API set, which really simplifies common use cases. So like if you want to use it for TLS, authentication, or you want to use it to just generate a key and export that key, or create a certificate signing request, or, do sealing on a key, or do a policy based on a sealed key. You can do all these with wrappers, and there's a bunch more of them. But some of the things, like, for example, we'll go into the parameter encryption. If you try to do it with the base APIs, it requires a lot of code. And we've set it up so that you could just call, one API to basically turn on parameter encryption for all of the activity underneath that session. The library is written strictly in C. It has no external dependencies. It uses no memory allocations whatsoever. So everything's on the stack. And there, again, no external dependencies. So we really designed it for embedded use. And as far as I know, this is the only TPM library that can be used in bare metal, and was designed for this purpose, right? Which makes it well suited for use in a bootloader. So the transport interfaces are SPI and I2C. Linux exposes a driver called dev. Well, it's the device interface dev/TPM0 usually. That has its own TIS in there, so it disables ours and it calls just command responses directly. Windows has a similar thing with a set of APIs. So it exposes a TPM through their TBS. I can't remember what that acronym stands for. APIs, and it's the same thing. You send a command, you get a response. From the Windows side, the TPM is actually locked down, so you cannot use the non-volatile storage. So if you create a key, what happens is the TPM wraps it with an encrypted blob and gives it back to you, and then you can store that, and you can load it, and you get a temporary handle to use it for signing. You basically doing everything. You have ability to do most things on the TPM, but you cannot use the non-volatile storage from Windows. And then there's also several TPM simulators out there. We can go into that if you want, but IBM has one. Microsoft has one. I think Intel even has one, but they use a TCP socket, and you start up the TCP server and you're sending commands and responses to same thing to the TPM. And the simulators are fully functional. It's really great. That's how I do testing on my Mac. I also have a Raspberry Pi with TPMs attached. So, and I have a couple that I can demo on both SPI and I2C. So the interface to communicate with the hardware, it uses a single IO callback for the communication. So you register that on initialization, and we have built-in support for all these things listed here, which is quite a bit. And then it's easy to add your own. I mean, really, it's just wolfTPM will give you a buffer that you need to send, and then the TPM will respond with it. That's kind of the essence of it. There's also an advanced IO option that gives you a little bit more detail, like if you're doing a read or a write, what the address is, and that has more to do with the TIS layer that's underneath it. Some build options, which we can go into. If you do configure dash dash help with autoconf, you'll get a list of enable disable options. We also have CMake support for wolfTPM in there. And let's see. And then I think there is also a small stack option. So the default buffer sizes are fairly oversized, or like 4K. But if you wanted to use a reduced stack size, so what I did was I came up with a minimum you need to do all the functionality that we expose. So that helps in cases where you have low stack memory. And then these are some of the debugging options you can turn on. And it'll give you more output. So this will show you more messages during operation, and verbose will show you some of the, I can't remember, it's like the next level command responses, and the IO will actually show you the bytes, which is kind of helpful if you're debugging issues. So yeah, and at the end, I'll do a Q&A. So how to use it. The native APIs are one-to-one mapping with the TPM commands from the TCG, and you have complete control over the arguments. It's a lot like what the TSS layer. So in a Linux environment, you have the TPM layer, but then there's usually the TSS layer on top of that. We did not implement that because it's just excessive. It does arbitration of processes across devices, and we're really trying to target embedded devices for what we do with wolfTPM. Yeah, so we took the complex commands and made them easier with wrappers. Yeah, okay. And so here's an example of just, initialization of a TPM, right? So the native API command would be TPM2 startup, and then I think it's self-test, not shelf-check. And we have an init wrapper, and it basically takes in a pointer to the device context. And the device context keeps track of some of the authentication settings. It also keeps track of the IO callback that was registered in any optional user context that's passed to that IO callback. And again, we have all of the built-in hardware support already available in wolfTPM in this HAL directory. And it does get included in the library. It can optionally be excluded at build time if you're going to register or create your own callback. So here's another example, which is creation of a primary key. The primary keys, when you create them, you immediately get back a temporary handle. They can be evicted to non-volatile, so they can be stored as permanent handles in non-volatile to save time. But for a primary, if you provide the same template to create it, it will create the same key each time. So usually, for example, the storage root key has a well-defined public template, and it takes a small amount of time to create those each time, but you need a primary to be able to do other operations with normal type keys that can be exported or used for signing. But this native API looks like this, and then we have one that's like create storage root key, which defines the template that's needed, and it gives you back either an ECC or RSA storage root key, which is the concept of an SRK goes back to the TPM 1.1 days, but it's really under the owner hierarchy, and it is a primary key under the owner hierarchy that's either ECC or RSA. And when you do parameter encryption, you can also bind it to the storage root key, that primary key for parameter encryption. Okay, let's go on. So here's an example 3 of creating like a standard key. So this one requires more details about the type of key and the template, and you can supply other additional attributes as well. When you create a normal key, the TPM always gives you back an encrypted, like I guess you could call it like wrapped, but it's an encrypted version of that key, and only the TPM is capable of decrypting that. And this is always the case. So it gives you back it, and then you would have to load it. At that point, you would get a temporary handle, and you could then evict that into permanent non-volatile storage and assign a permanent handle. But again, that consumes some of the non-volatile space. And for the TPMs that have a small amount of that, I mean, it's a small number of keys that you could store in there. But yes, that's how it works. And we've created wrappers to simplify that, so you can call a single shot API that creates it and loads it immediately. And there's different types of keys as well. Let's see. So here's just a code snippet for what it looks like to create a storage root key, to create an ECC key under that, which would then give you a key that you could do something to sign with. And we have so many examples in wolfTPM for this type of thing. And I'll go into those a little bit more. But it shows you how easy it is to do this. I think I also have an example for how to use parameter encryption. So if you're trying to do parameter encryption with the native APIs, it's a lot of commands and there's a lot of handholding about, for example, you have to have hashes of all of the names for authentication. In the wrappers, we handle all of that. So there's one API that just says, start a session, and then you set which session index is using that authenticated session, and you can supply parameters to turn on encryption and decryption. And the way parameter encryption works is the TPM and the device both derive a key, and based on a public key. And so with ECC, they do like a shared secret kind of computation. With RSA, they actually use the RSA primitive to encrypt it, pass it to the TPM. But nonetheless, there is a symmetric key that gets derived and is used for encrypting with either AES, CFB, or XOR. And the sensitive area of the commands, which is always the first argument of a command, gets encrypted, right? And certain commands support encryption because they know that they're sensitive or not. But the gist of it is that, and here's an interesting thing, is if you don't turn on parameter encryption and you do something like, I don't get RNG where you pass in some RNG, I mean, it won't encrypt that and it'll be in the clear over the wire, right? So one of the most common mistakes that people use in TPM is not turning on parameter encryption before they do sensitive operations, because it's not necessarily built in. Now, there is built in, if you take like an RSA private key and you try to import it, it does do an encryption mechanism in the process of doing that. So it doesn't encrypt secret. And so there is some protection there, but for the other commands, there isn't. So key duplication, key import does have some built-in mechanisms. Long story short, yeah, so this is what it looks like to start a session. So this one is bound to a storage key that was already created, which means it uses this public key to derive the secrets. It also turns on HMAC. So here you could either do HMAC or policy type session. And the HMAC provides integrity and authentication too as well. And then you have the option for CFB or XOR here. And then this is the session index. So some commands have password authentication that happens at index 0 and 1. So sometimes this gets moved out, but ultimately when you're building up the authentication command packet, it knows that you want to do parameter encryption on this session index, and you specify with these flags, right? So you say you want to do encrypt and decrypt. And these are inverse terms, so it's decryption from the TPM side. I think yeah. And the continue session means to basically keep it open for additional commands after that. This is the most common way. I turn on both for everything. Okay, so some real life examples. These are just a few of the many examples we have in wolfTPM. So, a secure key vault, being able to create keys in the TPM and protect them. You could also generate keys and load, export, import them. We have a great set of TLS examples for how to do authentication. We took it a step further too, and we actually support, with a build option, you could offload 100% of a TLS connection to a TPM. It does support crypto coprocessor activities, but it is not very good at symmetric. It can do symmetric things like AES and SHA too, but they're not very fast. And a lot of it has to do with the transport speed, right? SPI and I2C are just not very fast transports. So it's not recommended. It's not usually used for symmetric cryptography. It's usually used for asymmetric things like RSA and ECC. So we'll also talk about salient secrets, root of trust, attestation, and major boot. So this example is for the NVRAM and what it looks like to store something in NVRAM. There's a store read examples in there. Yeah, it might be easier just to show you guys. But then there's also key generation examples. So in here you can generate RSA, ECC, and symmetric type keys. There's also the ability to do export, import, and loading of the keys that you generate from there. I don't have one in here, but there's also a full example for doing a certificate signing request. So, for example, in TLS, your key also needs a certificate for authentication. And so in the examples, what we do is we create a key on the TPM. Then we create a certificate signing request based on the public key from the TPM. And then we have some scripts that let you either self-sign it or sign it based on a local CA. But you could then take that and get an official certificate for it from a CA provider if you wanted. And the certificate could be stored on the TPM, but usually it's not, because it's really just public information that gets sent out. But the private key does stay on the TPM. And then for the TLS, we have examples as a server and a client there. And I can demonstrate those. I'm set up to do that if we have time at the end. So for sealing secrets, when you create a key, it has the ability to also store sealed data. And you can store up to, I think it's like 1024 bytes. It's a pretty decent amount of additional data. Wolfboot uses this secret sealing feature to store like a disk encryption password. And we have that support in there. And usually you would seal it based on the state of the TPM's PCRs, which are basically registers that contain hashes that are measured throughout the boot process. But one of the things that happens is what's referred to as PCR brittleness, which is if something changes in the boot process, then the PCRs will change and then you can no longer unseal the data. So in TPM 2.0, they came up with a new scheme to solve this, which is you can seal data based on an externally signed policy. So you can, with an external key, you can sign the state of the PCRs, and then you can unlock the seal by proving that you have that. So you verify on the TPM, you do the verification of that signed evidence of the PCRs, and you check the PCRs, and that allows you to unlock it. So we did a ton of work to demonstrate that. It's very similar to what the Linux LUKS, the Lux disk encryption scheme uses. It's very similar to that. It's just taking advantage of a TPM feature. Also for a root of trust. So again, this is a really good example in Wolfboot, which we fully support. And the scheme that we came up with is to take the public key, hash it, put it into a platform. So it's a non-volatile index created under the platform hierarchy. And that is so that it can't be erased with a TPM2 clear. And then we set an attribute that allows it to be locked. And then after we've provisioned its TPM, we lock it. So that's how we can anchor a public key into the TPM. And then we do some other mechanisms for the pairing. So one of the cool things is when you create a key, and it gives you back that encrypted version, I mean, only that TPM, that specific TPM will be able to load it. And so that in conjunction with this is really good way to prove the TPM is the same one that you anchored to. Oh, and then in addition to that, we also, in the example with Wolfboot, we also have a password. So authentication is used with that MV index. Another one is attestation. So we have a great attestation example that attests to the timestamp on the TPM. So all TPMs have an RTC counter. It's a one-way counter, and you can advance the time counter. It's not RTC. It's just a uptime counter, basically. Oh man, I would love to show you that one on a real TPM. But you can actually create. So there's an attestation key that the TPMs have, and you can attest to something, which is basically a signed evidence of that. And you can do a bunch of other stuff with attestation. So we talked about Major Boot a little bit, but it uses those platform configuration registers. And throughout the boot phase, you can assign. So there's 24 PCRs. Typically, the ones that can't be reset by software are the first 16. I think this is by memory. They all get reset on a hard reset or power cycle, but you basically extend these PCRs, and then by the time the OS loads, you can read those and prove that the boot process hasn't been tampered with. That's pretty much how UEFI works. Okay. That took a little longer than I wanted. I would love to do a demo. There are a few questions that have come up in the Q&A. We could start that.
Yeah, perfect. I can read them off for you, David. So first here, what is the process for adding a new HAL? For example, to add support for free RTOS.
Yeah, so the wolfTPM library is not really dependent on RTOS. It really has to do with the hardware. So let's say you're using an STM32, I mean, or something like that, right? You're going to have a SPI or I2C driver. And I can show you an example for what they look like. So all of the so this is GitHub wolfTPM, and under the HAL directory, we have all the different example HALs. And for example, in ST, this top part here is the I2C implementation. And this is code generated from, I think we have a version for CubeMX HAL or the old standard peripheral library. I can't remember. And the one for SPI looks like this. TPMs have this, some of the TPMs have this thing called a SPI wait state, which is where you send 4 bytes and you have to wait till the TPM responds with the most significant bit set to wake it up. It's basically like a wake up sequence, and it may actually extend another 1 or 2 bytes. So there's a little bit of logic in the wait state, but ultimately all you're doing is sending sending a 5 byte header and then the remainder. That's really the extent of it. So, but this is really just an API that you register on an init. So any of our examples, for example, if we go to the wrapper test and we go to where the wolfTPM init is called, cryptocodecs. Oh, here. Yeah, we just pass in an argument. And the way that we set it up is this API specifically is the default HAL implementation that goes through this sequence. And we have lots of support out of the box and lots of examples. So again, it's not RTOS dependent. There's really nothing in the library that's RTOS dependent. If you want to have multi-thread support, there is a mutex that you could enable and use to protect concurrent access from threads, but that's really extent. Again, we don't use any malloc or free. The examples make some assumptions about the printf, but inside the library proper, printf isn't even used unless you have the debug turned on. So yeah, it's really minimal. Okay.
Awesome. All right. Thanks here. Next we got does wolfTPM support use cases for IEEE 802.1AR, IDEV ID, and LDEV ID generation, including any associated uh, attestation keys, AKs?
Attestation keys. Yeah.
Attestations.
Yeah. So
Yeah,
the TPM, the TCG guys put out a standard for manufacturer provision keys. They call them identity and attestation keys. So IDEV ID and I think that's what we're talking about. So IEEE 802.1 AR, that sounds more like the authentication of like Wi-Fi or Ethernet. I can't remember, but the TPMs, the manufacturer can optionally provision TPMs with identity, device keys, and certificates. And some manufacturers are doing this. I know ST is, for example, on their ST33. And I just put up a pull request for this specifically the other day for a customer. So on our wolfTPM page here, you can see add support for pre-provisioned device identity keys and certificates. And there's the specification is this one right here. It comes from, it's a public specification, and there's basically manufacturer pre-provisions a key and then creates a certificate that's signed by a trusted certificate, and that is stored on the non-volatile storage in the TPM, and they're given permanent handles, right? So the ST33, for example, puts them in a very specific place. So for example, yeah, so this is what ST defines their permanent handle positions are. I think that spec actually recommends something like that, but they could be anything. And then there's certain schemes for how to authenticate. But yeah, I don't know if that answers your question or not, but there's stuff there.
already. see here. Next, does wolfTPM support use cases for IEE? Oh, sorry, no,
You
that's
got
not
that one.
understood. uh, how does wolfTPM compare to other crypto devices such as the ECC 508? Can I use wolfTPM with ECC 508-608?
I love that question. That's a great question. So the at ECC, 608B, for example, which is Microchip's crypto coprocessor, ST has one, ST Safe A110. They are simple devices that all they do is like ECC keys for the most part. Some of the NXP has one like an SE050, but they're crypto coprocessors. They're very similar to TPM, but they're very reduced in functionality, right? So both the ones that I mentioned, actually all three of those, they all use I squared C. They have a certain amount of space that's very limited where you can create keys and use them for signing or even shared secrets. And there is some space to store certificates, and manufacturers do have ways to pre-provision those. The cost is typically lower, but every one of those chips has a different interface, right? So each vendor has their own SDK with their own command and response structure, their own encryption strategy for how to communicate over the bus. They're all different and they're not standard in any way. Now, could we expose wolfTPM and use it on the back end? We probably could, but again, it would be super limited. Like the APIs don't quite match up. I mean, you could expose an API that lets you create a key, like an ECC key, for example, and give you back a handle, which would be like an index of 1 to 16. But there's no concepts of hierarchy. There's no concepts of primary key. There's no concepts of any of those things, and so you would only be enabling a handful of TPM APIs. Yeah, I don't think it would be worth it. Let's put it that way. The value add for having the TPM APIs on top of it just wouldn't be worth it. Now, hopefully, I answered your question. I love that question.
Awesome. Yeah, next year, does Wolf also have a OpenSSL provider implementation for TPM?
Well, we haven't tried it, but we do have a provider implementation. It does use wolfCrypt, and wolfCrypt does support offloading to a TPM. So I've never tried it, but all the pieces exist, right? So wolfCrypt has a mechanism called crypto callbacks, and it's very similar to what OpenSSL provider does, but it basically registers a callback for all the cryptographic operations. And wolfTPM, we have, if you go into the source, there is a bunch of examples for both crypto callback and PK, which is public key callbacks, and it shows you how to do this. In theory, you could register wolfCrypt, register a wolfCrypt provider implementation. You could customize it to use a crypto callback with a TPM. I don't know why you'd want to do that, but you could. I've never tried it. I don't think anyone has. It's a lot of layers to go through. I do know that there is something built into Linux already that does it. I think that there is already a provider TPM interface. I want to say I saw that, but I can't remember what it's called. So yeah, feel free to follow up with, additional question, or even send an email to facts that's facts@wolfSSL.com.
Sweet. And then, yeah, I don't know if you want to read this next one. It's kind of
Sure.
lengthy.
So I need to manage more TLS sessions, each one with its own certificate and key. I want to use a TPM. The idea is to keep the key up on the file system, load them into the TPM when the application starts following the TLS distributed with wolfTPM registered crypto callbacks. Then you can pass all the handles, the private keys. The problem is I've not been able to solve is if there is a way to choose the right TPM key to use with the callback and both. Yeah, I mean, it's a complex question. I really recommend you email support@wolfSSL.com. But the implementation of the crypto callbacks that I was just showing you, it's not required that you use this code verbatim. You could pull this into your own library, because ultimately the set of APIs to register a callback are exposed. You don't have to use our implementation of it, but there is an opaque context pointer that gets registered as well. And you should be able to use that opaque context pointer to tell you which TPM sorry, which TLS session it is and which set of keys and certificates you want to use. That's just my 2 cents. But again, I recommend you email support at wolfSSL.com and get some support on that.
Awesome. And then next year, can I use wolfTPM with TPM modules already in my computer that Windows 11 requires, or do I need to separate one for my own apps?
Yes, you can. Yeah. So, well, as of Windows 11, TPMs are required. You have to have a TPM. And so Windows exposes an API set called TBS, right? And we fully support that. And we have many production customers using wolfTPM on Windows. And we even have a Visual Studio project for it. It makes it really easy. I would love to demo and show it to you. I'm not prepared to do it, but I do have a Windows machine with a TPM. And we test that. We have production users on it. All the examples are there. So the only limitation is what I mentioned before, which is that you cannot use the non-volatile storage on the TPM. That's not something the Microsoft exposes. And they actually do that through what's called a locality. So the TPM at the user level gets started with a different locality so that it's prevented. It's just not allowed. And there's a lot of good reasons for that. If the user had the ability to fill up the non-volatile storage, then the TPM would get into an undetermined, unusable state, right? So that doesn't really limit. You can do just about everything with a TPM not having an NV. You just can't put anything into permanent storage on the TPM, but you can create keys and get back that key reps, that encrypted version of a key, and you can load it and you can get the temporary handles and you can use that. So hopefully that answers your question. And I mean, I think there is a whole section here on Windows TBS that talks about it and ways to build it. But there is also now Visual Studio projects for that too. So you can build all of wolfTPM from Visual Studio and test it. And that example that I was showing, the wrap test is in there. And the TLS server example is in there too. That's right. And it's pretty slick the way I set this up because you just load up this solution and it'll build wolfSSL, it'll wolfcrypt test, and all of the build settings come from this one configuration file for Visual Studio. So, and if you were going to use FIPS Ready, you could turn that on too. Yeah. Any other questions? Oh, right.
One more popped up here. Do you have an ESP32 TPM example?
I don't think so. It would be pretty easy. Our ESP expert, Jim Scarletta, Go Jimmy Pie, is on this chat. So feel free to pipe up if you have actually done a wolfTPM port. I cannot recall. So he's attending, but is it possible to make Jim Scarletta speakable?
Yeah, I can do that.
Yeah, talking permitted. Yeah, if you want to answer that. I don't think it is, but which specific ESP32 target? I would love to know which one you're trying to use. Is there any other questions while we're waiting?
Hey, David, can you hear me?
Yes.
Yeah, no, I have not implemented any TPM for the ESP32.
Thanks for confirming. That's what I thought. You just need some TPM hardware and you'd do it, I'm sure. All right. Well, I don't see any other questions. Cameron, you want to wrap us up?
Yeah, of course. Awesome. Yeah. Thank you, David. That was a really informative webinar. I know I learned a lot myself. Thank you everybody for taking the time out to join us. I'll be sending a copy out of the webinar and can provide PDF slides if needed. Please don't forget to follow us on Twitter at wolfSSL. There you'll learn about our upcoming webinars as well as our blog posts. And feel free to connect with us on LinkedIn and subscribe to our YouTube channel. And if you do have any other questions, feel free to shoot us an email at facts@wolfSSL.com. And yeah, thank you again, and we'll see you next week.